Good morning, everybody. My name is Steve Sorch. I'm PAC International Sales Director, and with me today is our INCE board certified acoustician, Mike Raley. Mike Raley is going to be presenting Designing Higher Acoustic Performance for Fitness Spaces. And before we jump into the presentation, a little housekeeping here. If you have questions during the presentation, please put those in the Q&A, and we will try to cover those at the end. And without further ado, Mike, go ahead, take it away.
All right, thanks, Steve. Yeah, so we're going to talk about designing higher acoustic performance in fitness spaces. So kind of just going to go through a number of different areas where PAC products work and like kind of the shell of a fitness space, and some things to deal with. Better acoustical performance really focused on sound transmission, sound isolation, not sort of interior room acoustics. And this comes from, my experience. Started working on fitness spaces as an acoustical consultant, where I kind of got into doing heavy hard impact testing, so dropped free weights, this kinds of stuff. And then prior to PAC, worked for a manufacturer of fitness flooring, and now I've worked at PAC for a number of years and working on developing ASTM test standards for heavy hard impact testing and all of these different things. So just kind of some of my thoughts here on the different areas and application for PAC products. If you've got any questions, put them in the Q&A. I think I'll try and make some time for questions at the end of this, and we can kind of have some discussion too. All right, so with that, we'll get into this. Let's see which way okay, so just overview of what I'm going to talk about. Talk about floors. It's kind of been the primary focus of this. Talk about some kind of typical acoustical options, just different categories of floors for acoustical performance, and then some other design considerations besides acoustics. Design considerations outside of acoustics always matter for everything we're doing, but in gyms for floors, like floors are a big part of the function of the gym, especially these days with more functional training and things like you see the green sled lane there in that image to the right. So we're going to talk about those other kind of design considerations: aesthetics, layouts, function, durability, these kinds of things. Then we'll talk about ceilings, ceilings above gyms, which is usually primarily for airborne sound isolation, and then also ceilings below gyms, where we're typically looking at airborne and impact sound isolation. And then last, we're going to look at walls. We'll talk about sort of just direct sound transmission through the walls, then direct impacts on the wall, somebody throwing something at the wall, and then flanking, controlling flanking, and that's just how sound propagates through the structure and kind of goes around the sort of sound barriers that we've put in place. All right, so let's start with flooring. So in flooring, we have kind of a wide range of different options. And from an acoustical standpoint, if we're trying to reduce impact sound, we typically try to go towards softer flooring products, right? Because softer typically means more isolation. And if you think about, you as an impact, like, like my daughter's now in like a tumbling class, right? And so they've got these big, thick tumbling mats. Like if you're going to fall on the floor, the thicker and the squishier it is, right, the more it's going to reduce that impact. It slows down the force, it widens the force pulse, and there's less of like an abrupt force on you or on the floor itself. But softer doesn't always work for a lot of fitness functions. So like cardio, if you've got a floor that's too soft and you're on a treadmill, right, it starts to rock, it feels weird, it can mess with your gait, right? I was once at a project where there was a Stairmaster on a very soft floor that worked great acoustically, but if you weren't really sort of balanced and stable on the Stairmaster, the thing started tipping. It was really scary. The image there in the middle, sleds, right? If it digs down too much, you're going to get too much resistance. It's going to really be hard to push. Could create damage to the floor if something gets caught there. Heavy lifting, right? If you've got people that are doing performance lifting, strongman competitions or weightlifting and these kinds of things, right? If the floor is not stable enough, you can get rock when you're, at your maximum trying to lift something. If the floor is a little unstable, right, you could really hurt yourself. Ankles, get all kinds of different injuries and things. So there's a lot of different considerations that are really important for the function of the floor, besides just the acoustical performance of it. So how do you balance all of these things? The aesthetics, a lot of these are going into high-end spaces, condos, apartments, hotels, things like that. And all the different function, durability, these floors that get a lot of wear and tear. So on the aesthetics side of this, right? I mean, I used to work for a manufacturer of rubber sports flooring. That works really well in a lot of ways. I mean, one, rubber has high friction, coefficient of friction, even when it's wet. So if you've got places where people are, sweating and stuff like that, it's gross, but like floor gets wet, it doesn't get slippery. It's not a slip hazard. Like that's a big deal in a gym space, right? It holds up well to a lot of abuse. It's softer, and you can adjust how soft it is to get, different variations of, acoustical performance versus other functions for it. But a lot of times the designers don't like the look of it. Now there are some places where they do like it, like this image on the left, it's kind of a more industrial kind of look. And that can work great for some spaces. But a lot of times designers, especially for, like hotels and apartments, condos, things like that, they want this sort of cleaner, modern, fresh look like that on the right. So a lot of times they'll go for LVT or Chillowich. The image that I had before, it was kind of like a Chillowich kind of patterned floor. So the designers want this look, but then how do you blend that look there on the right with actual acoustical performance? You can't just put LVT on top of a bunch of rubber. One, the LVT manufacturers will not warranty that. They're really hesitant to warrant it even on like 5 millimeters of rubber, let alone 2 inches or something like that. And there's reasons for that. Like if the substrate of the LVT can deflect, then the LVT gets stretched when you put weight on it, especially a concentrated load like the foot of a treadmill or something like that, and you can get permanent deformation of that LVT. And then you go and you move equipment, and you've got this big eyesore of a gouge there. It's like moving your couch on your carpet in your living room or something. And I'll show an example of that from a project I saw earlier. So how do we do these things, right? Aesthetics, something to pay attention to. Also layouts, right? So we have a lot of different types of spaces and functions within a gym. How do we get the right kind of flooring for all of these different spaces, right? So maybe an LVT with a thinner underlayment or something like that could work for places with cardio, treadmills, something like that. But it's not going to hold up, and it's not going to provide enough sound isolation in a free weight area. So sometimes you'll see these different kind of zones, right? So here in this image, you'll see that they've got this kind of LVT area here for a lot of the space, but then in the free weight area, they have this kind of rubber flooring or something like that. And it looks like it might actually, there might be a little bit of a ramp up here. So maybe this is over top of the LVT or something like that. This is nice because you can use different floors that do different functions. Well, also this creates a zone of sort of a visual designation of like, here's where you go do free weight stuff, right? And that can be really helpful. But you have to figure out, how do you manage these? How do you create smooth transitions between these? We'll often go for thicker floors for these free areas. Sometimes these like molded rubber fitness floor tiles will be 2.5, almost 3 inches thick. Well, then if you have to transition down to a thinner LVT floor, you might be transitioning down 2.5 inches. Well, for ADA, the ramp requirements are 12 inches of run for 1 inch of rise. So if you've got a 2.5 inch thing, you've got a 30-inch long ramp. So how do you make space for a 2 foot, 2.5 foot ramp in a space like this? Right? That can become really challenging, often when you're trying to cram as much equipment as possible into these spaces. So you really have to pay attention to these kinds of things. Sometimes people will, this one here kind of looks like an afterthought. Again, I saw a bunch of people asking about Chillowich. It's this kind of, it's a brand name, I think, but it's something that a lot of designers were interested in. Maybe that ship has already sailed. I don't know. It's just the flooring look. So in this case, they've just got some kind of rubber little area mats over here for this free weight area. So this is thin, so it's not going to provide that much acoustic isolation, but it's still thick enough to like be a trip hazard, especially like over the years, people kind of bump into this. Maybe the curls or the edges and corners kind of start to curl up, right? There's a potential trip hazard here. Also, you can get some chemical reactions sometimes between the plasticizers in some rubbers and like vinyl, things like that can create yellowing in the vinyl, right? So there's all these sort of like different material compatibilities that you have to pay attention to. So these spaces are really complicated when you really dig into all the nuts and bolts of trying to lay out the flooring in a gym like this. It can be really complicated to get something that both works acoustically, aesthetically, functionally, and deals with durability. And on durability, so here in the middle is kind of just this and function, right? So here in the middle, this is just a stock image I found when putting the presentation together. So you've got, looks like a sort of a molded rubber tile here, but then you've got this sled lane, right? And so you'll have things like this where you need something different that you can push a sled on, right? So the rubber tends to have a high coefficient of friction, so it's going to be sticky. It's going to be hard to push a sled on it. Usually they'll use turf. And you can put turf on top of rubber sometimes, things like that. Also, this is just, clearly designated, here's your sled lane, right? Rather than somebody just going and doing it wherever, creating kind of wear and tear on the floor in all these different places, creating conflicts with other, gym patrons, these kinds of things. So functionally, we can give visual designations with different floor types that serve different functions. From a durability standpoint, the one on the left, this is a picture I took. This was a nice high-end hotel in Toronto. This was in their gym. This was, I think this was like a sheet vinyl floor. You can actually see here, there's a little bit of like a heat, I think this is a heat welded seam. So it was some kind of, I think, sheet vinyl. And it had, I don't know what this was exactly, but I think it was something that just had a thin, maybe a thin foam back, maybe just a couple millimeters or something like that. And you see here, this is the leg of a piece of like selectorized weight equipment, the ones with like the stacks of weights where you move the pen. And here is where this had just moved a little bit, and you can see this big indentation here. Like this is probably plastically deformed and not gonna come out ever, right? Like it's just permanently like this. And you can see there's even another little dent here, maybe some discoloration over here. And we were there, like one of the hotel managers or something brought us in to kind of take a look at this and suggest other options. But they liked the look of this, right? They wanted to maintain that look, but have more durability and better acoustical performance. The image on the right here, this is rubber on top of a really thick buildup for acoustical purposes. And this was a apartment project, I think in Maryland. And acoustically, like there was an apartment below this gym, and we went and I did some free weight drops and things. Acoustically, this worked fantastically. It provided a lot of sound isolation. You could still kind of hear it in the space below, but it was very muffled. But functionally, this provided a lot of issues. So this was the space where we had the Stairmaster on it, and the floor was so soft that it wobbled back and forth quite a bit. And this is one of the feet at the front of the dumbbell rack. And you can see that this is sunk in. I mean, it had sunk in half an inch, maybe an inch. Like this is completely, this little foot here is completely depressed into the floor. So acoustically, this floor functioned amazingly, but for durability, supporting the weight of these things did not function. So how do you balance between all these different flooring choices, right? Sort of the aesthetic choice of the designer on the left, and maybe sort of more of the acoustical choices, so thicker rubber floors or maybe floating floors on the right. So on the right, what we have is a sort of an example of the buildup underneath a floating floor, where we have the little sort of blue squares here are acoustical isolators. In this case, these are the PAC IFB. It's a 2-inch by 2-inch foam block that you can get 1-inch or 2-inch thickness. You sort of lay them out as a grid, and then you can put insulation in between them. Here, the contractor actually used, I think this is mineral wool, and they actually cut little holes in it. You can also just run fiberglass bats in between these, and that works just fine. That's the way we've acoustically tested these. But so then on top of this, you can put a couple layers of plywood and then flooring on top of that. Or you can put plywood and then pour concrete on top of that if you need one additional mass for better acoustic isolation. And a floating floor gives you sort of a rigid floor substrate that you can put, rubber or vinyl or, these different floor finishes on top of. And because they're going directly on plywood, they'll hold up. You won't get the deformation as much, these kinds of things. But then you have your acoustic isolation below. So that can work really well for a lot of these spaces. But you are putting a rigid substrate right at the impact area, right? So for the same thickness of like plywood on top of an isolator compared to just the same thickness of just rubber or rubber and foam, something like that, you won't necessarily get the same level of acoustic isolation. So again, this is a balance in performance. So floating floor systems, typically when we're providing acoustical data for floor ceiling systems, we'll provide two numbers of the way that these tend to be specified. Is an STC rating, that's the sound transmission class, deals with airborne sound isolation. And then also the IIC rating, which is the impact insulation class, that deals with impact sound isolation. We have two other metrics, the newer metrics that are related to impact sound. Those are the HIIC, which stands for high frequency impact insulation class, and then LIIC, which is the low frequency impact insulation class. These are all useful metrics. They have their own nuances to them and their applications and their uses and things like that. I have other presentations to talk about those, including an AIA accredited webinar. You can go check that out. But the important thing for fitness spaces, for gyms, the important thing to know about these ratings, the IIC ratings, is that they don't really apply that well to gyms, because these are the way we generate these is we have like a tapping machine, and it has these little weights that are dropped from, I don't know, maybe an inch above the floor surface, and the weights weigh like 1 kilogram. So it's a very light impact. It's decent for representing footfall, but it is not at all sufficient to represent somebody dropping a free weight, even if it's just like, a relatively light dumbbell dropped from a few inches, like at the end of, your set, and you're just tired, and so you drop it the last little bit, right? That's a much bigger impact than what's generated by the tapping machine. So the tapping machine is not a good representative of those. So if you're trying to design or specify a fitness space, don't really rely too heavily on these metrics. They can lead you astray. Unfortunately, we don't have other metrics yet. I and a number of other folks are working on that, test methods and metrics. But what we do have right now is sort of a base methodology is we do heavy hard impacts. So we will drop a heavy hard round weight, typically from 0.5 meter onto the floor, and then we'll measure how loud the sound levels are down below in the space. We can also measure vibration levels, which I'll talk about in a minute. So here we have, this is really for the acousticians. On this, if folks have questions about this, I can spend more time kind of explaining these graphs later. But so this data here, the graph is dropping a 16-pound shot put onto the floor. So we always have a rubber floor surface just to protect the concrete slab, so we don't like chip it or damage the laboratory slab. So we have a 6-inch concrete slab. We drop the ball on top of this rubber, and then we also, that's the blue line, and then the green and the red lines are, we have the 6-inch concrete slab, then we have a PAC IFB floating floor like I showed in that image before, and then the same rubber on top of that. So you can see that putting the IFB, those floating floors, dramatically reduce the levels. So on the horizontal x-axis here, we have frequency from low to high, low on the left to high on the right. And then on the vertical y-axis, we have the measured sound pressure level at each different frequency from low to high. So here, lower numbers are better. It means it's quieter, right? So you can see that for most of this range, right, we have these very high levels here. In blue for just the concrete slab with the rubber on top. And then when we add the floating floor, these levels drop dramatically. So this is a huge reduction in the impact sound levels down below. But I've compared these, I've talked about comparing these floating floors to like a rubber floor, right? And that's a common go-to for acousticians to recommend. So how do these compare? So I don't have laboratory test data that does that, but I do have these vibration deltas. Now, if you're not familiar with the vibration deltas for impacts, again, I have a whole presentation on our PAC IFB. There's webinar recordings on our website. Mike or Steve can put that in the chat for you guys, link to that video. The whole somewhat complicated thing. But basically what we do is, so this is the tapping machine. I think I saw some notes popping up that folks are talking about the tapping machine. So it's this little tapping machine. Again, it's got these little metal weights in it, and they just get dropped down and they tap on the floor. Tap, 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 tap. And we measure typically how loud it is in the space down below. Typically, we're doing this on a floor with a room above and a room below. In this case, we don't have a room below because we're just doing vibration measurements. So what we did is we put the tapping machine, or for fitness spaces, we had a shot put. I just don't have an image of it here. Had a shot put. We dropped it onto a piece of rubber directly on this concrete slab. This is the PAC warehouse. So we dropped it onto that, and we measured the vibration levels on this concrete slab out here, right? And then we put our floating floor in place, either concrete or plywood. We dropped the shot put or put the tapping machine on this floor, and again measure the vibration levels over here. And then we took the difference between the two. So we saw how much did putting the floating floor in place reduce the measured vibration levels on this concrete slab. And I've done work to show that you can use that to predict like the laboratory sound pressure levels, and a number of other folks have also done a lot of work on this. And it's kind of a direction I would say that the industry is moving for these kinds of things. We tested a bunch of different configurations and things like that. But for the purposes of this, these are the vibration deltas. So the reduction in the vibration levels. So here, bigger numbers are better because it means more reduction. Okay, this is for a 16-pound shot put. Here again, on the x-axis, horizontal axis, we have low frequencies on the left, high frequencies on the right. And then on the vertical y-axis, we have the reduction in the vibration levels, which is fairly well correlated with the reduction in sound levels. Okay. So you can see that generally as you go up in frequency, you get more reduction. That's pretty typical. Low frequencies are just harder to isolate. We tend to get more isolation for both airborne and impact sound as we go up in frequency. These different lines represent the vibration deltas, the reduction in vibration levels for the different floating floor options or different flooring options. So the red is 2 layers of plywood on the 1-inch PAC IFB, the 1-inch PAC foam isolator, and these are loaded, so it's got some weight on it, all those sandbags. Then the purple line here is again 2 layers of plywood on the 2-inch PAC IFB, so it's just a thicker foam isolator. The orange is a 64 millimeter, so 2.5-inch thick molded rubber tile. And then the blue line, light blue line, is a 4-inch concrete slab on the on a layer of plywood like formwork on top of the 2-inch PAC isolators. So you can see that if you have just a really thick, squishy piece of rubber, it does provide more impact sound isolation than, you know, the plywood on top of the foam isolators. But again, functionally, there's a lot of advantages to having that plywood substrate. So for cardio, weight machines, a lot of different things, even for heavy hard impacts, sometimes, depending on how big those impacts are, the plywood on the 1 or 2-inch IFBs may be sufficient. Sometimes you need more than that. So maybe in a specific free weight zone, you have the molded rubber tiles that are 2.5 inches, and guess what? 2 layers of 3/4-inch plywood on the 1-inch IFB is also 2.5 inches. So you can start to kind of create these fairly level floor surfaces. You don't have big transitions that you have to deal with. And the different floor surfaces, again, can be designations for, you know, the rubber floor can be your zone for here's where you go do free weight stuff. And then the rest where you've got the plywood, you know, IFB system, you can put LVT or something on top of that. And that's, here's your other area, right? But if you really need higher levels, yes.
Sorry to interrupt. Somebody asked on the purple and red lines, is that bare plywood for the 16-pound shot put vibration delta, or was there something over the plywood?
So for all of these, whenever we're doing these impacts with the shot put, we're always putting some sort of a little rubber bit. And so in this case, this was like a 10.5 millimeter piece of rubber that was on top of these. So we use that consistently. Like we use that when we do the impact, you know, directly on the concrete slab. So we don't want to, you know, chip our concrete slab, damage our concrete slab, or, you know, dent the shot put. So we put a piece of rubber there. And then to get consistent results, because the rubber does have some impact isolation to it, we also put that rubber on top of everything else that we're testing. So the shot put is always hitting the same surface initially, which is that rubber piece.
Great, thank you.
Yeah. And again, I have a whole presentation or maybe a couple presentations on these. I think I saw you guys put links to it. So there's a lot more. I go into a lot more of how I do all of these deltas and things like that there. But here, if you look at this blue line, you can see at the very low frequencies down here, it got significantly more isolation than even this 2.5 inch, thick rubber tile. So there's a lot of options here. I know of like throwing out a lot of terms and all these kinds of things. There's a lot of ground to cover here. So I think if you're going to take anything away from this, floors are complicated, just really for any kind of space, but for fitness spaces especially, we ask a lot of our floors. They are part of the functional system, like sled lanes and things like that, right? We have a lot of sort of different acoustical requirements for the different use types that we have. Heavy hard impacts are really hard to isolate, so we need to do a lot of work. Just LVT on a little foam or rubber pad is nowhere near sufficient to isolate, even just a little dumbbell dropped from half a foot off the ground. And we have a lot of different sources, and so there's no one size fits all solution for these. So you really need to dig into these, both the functionality of the gym and the acoustical requirements, and to try and find the best options. And you may use multiple solutions in one gym space, even a very small gym space. And so if you're working on these kinds of spaces and you're like, whoa, there's a whole lot of information, reach out to us. Let's have a conversation. I'm happy to work through all of these things with you, review your own plans, and help you kind of figure out which directions make sense for these things. All right, so floors, I'll try and get through ceilings and walls, and then hopefully have a little bit of time at the end. We can come back and answer some of the questions that have come up. All right, so ceilings. So typically when we're looking at ceilings for gyms, we've got the ceiling above the gym. And for those, typically we're looking at isolating airborne sounds. So whether it's clanging weights or you've got music playing in the gym, whether it's sort of just like background music, or maybe you've got a spin studio like this, where they've got the sound level cranked and it's really loud and you have to provide a lot of sound isolation to a space up above. For the ceiling below, we're often dealing with, airborne sound isolation, just like going up, but we're also dealing with impact sound isolation, right? Because you're impacting the floor, and then there's often something below it that we're trying to isolate. So for ceilings, when we're trying to get high levels of sound isolation, both for airborne and impact sound, acousticians, our go-to is typically spring isolators. Because they provide high levels of sound isolation, and especially higher levels of sound isolation at very low frequencies, which tend to be the biggest issue and hardest thing to address in fitness spaces and a whole bunch of other spaces too. So at PAC, we have a whole bunch of different spring options. We can kind of combine them into two categories. So one would be side mount. So these would go to the side of a joist or a truss. So, dimensional lumber, 2x10, a wood I-joist, or a wood open web truss. These can also go to the side of a steel C-section joist. Got a lot of different options, a lot of different ways to mount these. Often when you're dealing with these joist structures, the drywall ceiling is part of the fire rated assembly. It is really like the primary part of the fire rated assembly because it's what protects the structure from the fire down below. And so then whatever is holding that drywall is also an important part of the fire rated assembly. So it needs to be listed in a UL design or some other approved, fire rated design if there's a, 1 or 2 hour fire rating requirement for this assembly. PAC's springs on the left here is the Rizik SI1 Ultra. On the right is the Rizik SI-CRC Easy. There's some different construction variations in them. Again, I've got another webinar all about our springs. You can go check that out for more details on these. But these are in, like an order of magnitude more UL designs than sort of the other competitors. So we've got a lot of different options to kind of work for most projects. So that's side mount if you've got joist structures. The other option is top mount. So this is typically you're going underneath a concrete slab, right? Or maybe it's concrete on metal deck, right? Usually sort of a monolithic thing where you're mounting it to the bottom of it rather than to the side of a joist. On the left here, we have our Rizik SI-CRC2. This is our low profile spring. You can just think of low profile spring. So this will go down to like a 4-inch air cavity. And then here we kind of have our more standard spring. This will start at maybe about like a 10 or 11-inch cavity, but say about a 12-inch cavity, and then we can go pretty much as deep of an air cavity as you want. And that's between the concrete and the your drywall ceiling. We've got a bunch of different attachment options, kind of work with however the contractor and the architect want to attach this and build this ceiling. These typically don't need to, the concrete is typically your fire rated assembly. That's the fire barrier. So the springs and the ceiling below don't need to be part of that fire rating assembly. So we and others don't have fire ratings for these. So springs, we're going for high levels of sound isolation. And testing things with high levels of sound isolation can actually be really tricky in a lab because sometimes the labs just can't measure as high as our assemblies go in terms of sound isolation. And that's another conversation. But just recently, we had the good fortune to work with the great folks at Maxon. They have their own in-house lab that is NAV Lab accredited. And just a couple weeks ago, I was there at Maxon doing some testing. So now we have some new test data for our springs. I have sitting in my inbox draft test reports to review, make notes on, and so hopefully we will have those full reports and all this data out very soon. It'll be on our assembly selector for those of you that are familiar with that, where you can go access it. So here, another graph. For those of you familiar with these, you'll see what's going on pretty quickly. But for those of you not familiar, again, like with all of the other ones, on the horizontal, the x-axis, we have low frequencies on the left, high frequencies on the right. And here on the vertical y-axis, we have the transmission loss, going from no transmission loss to very high levels of transmission loss, the higher numbers. So higher numbers are better. It means more noise reduction from one side to the other, right? So the blue line here is the transmission loss values for just a bare 6-inch concrete slab. No finished floor, nothing on top, no ceiling below, just a 6-inch concrete slab. And then here for the green line is an industry standard spring, so a 1-inch deflection steel spring mounted to the bottom of the concrete slab, and then 2 layers of 5/8-inch Type X drywall for the ceiling, and we had about a 12-inch, I think maybe it was like a 13-inch airspace, something like that. Excuse me. So green line is an industry standard steel spring, and then the red line is the PAC, one of PAC's springs, the image that I showed before. It's the Rizik SIFF 3/8. And so you can see at low frequencies down here, the two are essentially the same. This is within sort of testing variation, so no real difference. I think we're also still kind of approaching the flanking limits of Maxon's lab, kind of the limits of what they can measure. We're kind of getting there. I'm not sure if we're like right up against it yet, but here at mid and high frequencies, you see the separation. You see that the PAC springs actually perform better. And I think that is a real difference. We get some variation in testing and things like that. So small differences, like you see down here at low frequencies, I wouldn't put too much stock in those. But these are big enough differences here that I think these are real differences. And the reason for this, I believe, is that the PAC spring has, we have the steel coil spring, right? But then up at the top of it, we also have a rubber isolator. The other spring we tested, my recollection, does not have any significant rubber isolator in it. And so you are seeing better high frequency performance because of that rubber. So ceilings below gyms. So one, ceilings below gyms can get kind of complicated, right? Like architects like to have some textual variation, so they'll vary their ceiling height. Here we have this bare exposed concrete and then a very thin soffit here and then a little bit deeper soffit here. We also have a light in the ceiling. We have this light hanging from it, right? Now, don't leave exposed concrete directly below a gym when you have a nice apartment or condo like this. You need an isolated ceiling to really get good levels of sound isolation, so you're really not bothered by those impacts. So I would suggest drywall all the way across. You could still get this surface variation, but just drop it down a little bit. Excuse me. But we can do all of that with spring hung ceilings. We can get pretty complicated with our spring ceilings. We do full shop drawings for our spring ceilings. Here's kind of a detail, and again, I'm not going into all the details of this. I have another webinar. We have a lot of webinars. You should check out our webinar page. We have another webinar that talks about ceiling details for good acoustics. That's another AIA accredited webinar we can do. And we go through some of these details. So we could do a spring hung ceiling with drywall for sort of your main acoustical noise barrier. And then below that, we can drop, an ACT, we can do acoustical clouds, secondary ceiling to hold mechanical, all of these different kinds of things. So we've got a lot of different options here. And we can accommodate those kind of ceiling height variations and things too. So if we're looking at a gym above some sort of noise sensitive space like that apartment, we're concerned about airborne sound transmission. That was the transmission loss values I showed just a minute ago. But we're also interested in the reduction in impact sound going down, right? Whether it's somebody, running on a treadmill or it's a dropped weight, right? And think about it, you're dropping the weight right on the floor, and then right below it is that apartment, right? Somebody trying to sit there and read or work from home or whatever it is, right? If you keep hearing these thuds from above, that's going to be very disruptive. So how much isolation do we get from a spring hung ceiling when we have a heavy hard impact? And I may be forgetting something, but I'm not sure that I've seen data for heavy hard impact on a spring hung ceiling. And there's a lot of caveats that go to this data, but it's nice to see sort of the comparison and the amount of reduction that you actually get. And I may be missing somebody that's presented on this before, but I think this is useful information to have. So again, this is a 16-pound shot put. And in this case, just like the other ones where I talked about where we dropped a 16-pound shot put, we did have a piece of rubber. In this case, it was a 9mm piece of PAC's, rubber underlayment. So we impacted on that. Then we had a 6-inch concrete slab. I think I saw somebody ask a question, was this a normal weight concrete slab? Yes, this is a normal weight concrete slab. So piece of rubber, concrete slab, and then again, the spring hung ceiling. So spring hangers. We had some insulation in the cavity. I think I forgot to mention that before. And then 2 layers of 5/8 Type-X drywall for the ceiling. And then we measured the sound pressure levels in the room down below. So I would not pay attention to the absolute sound levels here. Really, the thing to look at is the reduction in the levels from just the concrete slab to the concrete slab with the spring hung ceilings, and also the comparison between the 2 springs. So here again, the green is the industry standard spring, and then the red is the PAC spring. And you can see that again, at low frequencies, they're essentially identical. But even down to 50 hertz, we are getting a pretty good amount of isolation. So this is great. Spring is really isolating all the way down. And the reason we pick springs, like I said before, is because they should provide good isolation at low frequencies. And here we see them isolating down to 50 hertz. Somebody asked, what is the depth of the air cavity? I think it was about 13 inches. We can come back and confirm. I think Mike knows the dimension. We'll check on that at the end, or Mike can put it in the chat. And here you can see that at mid and high frequencies, the red spring, the PAC spring, did better. So this is the same thing we saw with the transmission loss values. We saw mid and high frequencies, the PAC spring provided more isolation, I think because of that rubber. Same thing here for impact sound. And you can see just really big reductions all the way across the board. So spring hung ceiling really does work to give you that good isolation below a floor where you've got heavy hard impacts. All right, last thing here, walls, and then we should have at least a few minutes for questions, and I'm happy to stay on for a bit to pass the hour. So walls. So a few things to consider with walls. One is sound transmission, right? We use SDC ratings for this all the time. Something to consider with SDC ratings is SDC ratings really don't take into account like low frequency, like subwoofer kind of frequency sounds. They stop the 125 hertz 3rd octave band. So all that like kick drum and bass guitar stuff, or just, electronic, all the low bass, not really accounted for by an SDC rating. So as acousticians, if we're designing for a space like a fitness space or like a spin studio where we know there's going to be a lot of like low frequency energy, spin studios will often have subwoofers. You really like feel that bass to like motivate you, I guess. acousticians will not just look at an SDC rating, but they'll look at like the actual third octave band transmission loss data, like I showed, and then they'll kind of do calculations based off of that to make sure that they've got enough isolation at low frequencies. So here we've got, this is a typical apartment building. This is actually one we did springs for this ceiling. This is why I have the drawings for it in this gym space, because there's a unit, an apartment directly above it. But here we've got this wall. And so here's this fitness space. And then here's an apartment. And right here is a bedroom. And if you think about typical layout, there's another furniture plan. The bed is right here. So your headboard's right here. So your head's here. And then in the gym, there's your cardio and then your free weight area. So you can imagine somebody going and putting their free weights back on this rack, you know, little metal clanging and things like that, all of this kind of stuff, all this noise right here. So we need good sound isolation here. And the way that this wall is drawn, I believe this wall is a double stud wall. So that's two totally separate sets of studs and top and bottom plates with typically a 1-inch air gap in between, no rigid connections between them, other than maybe like the structural framing at the top and bottom. But even the top and bottom plates are separate from each other. And then, you know, drywall or whatever on the sides of the studs. That's commonly what we do. And I think most acousticians, myself included, typically think that, you know, based on test data, that double stud walls provide better sound isolation, especially better sound isolation at low frequencies than do clips and hat channel, like the PAC RISC one, right? It's sound isolation clip with a rubber isolator, and you put hat channel into it. So clips on a single set of studs. However, the question is that because the two totally separate sets of studs just provides better isolation efficiency, so just less transmission at low frequencies than do the clips? Or is it because a double stud wall, typically, you know, like 3 5/8 steel studs with a 1-inch airspace, that's a 8 1/4 inch wide wall, 8 1/4 inch air cavity, whereas the RISC clip and hat channel on a 3 5/8 steel stud is a 5 1/4 air cavity. So there's a 3-inch difference. So is the difference in low frequency performance because of just isolation efficiency, or is it because of differences in airspace? So my good friend Ben Schaefer at Papco Gypsum goes and does a whole ton of testing. So the wall at the top is his test. It is 2 sets of 2.5-inch steel studs with a 1-inch airspace, and then, you know, a layer of 5/8 Papco Type X gypsum board on either side. So that's a 6-inch air cavity. And then the one on the bottom is a PAC test that we did, sort of in collaboration with Papco. And it is a 3 5/8 steel stud. These are both 33 mil steel studs spaced at 16 inches on center. So trying to control as many variables as possible. Then we've got the RISC clip in the hat channel and Papco Type X gyps on either side. And that's a 5 1/4 inch. So these are much closer, only a 3/4 inch difference. And we get the same SDC rating, which that's good, comparable performance there. But I just said before that SDC ratings don't include the low frequency stuff that we really care about for these kinds of fitness spaces. So let's look at the TL curve. Well, there's very little difference between these. Here, the mid kind of frequencies around this dip, there is some variation, you know, maybe there's some real variation here, but it's small, just maybe a few dB, not really a noticeable difference for the most part, I would say. And then down here at very low frequencies, 80, 63, and 50 hertz, we do have some variation. Now, low frequencies, we're going to get more variation in our measurements anyways, so some of this is just test variation, not necessarily real differences between these. At 80 hertz, maybe that's enough, or there's a little bit. But point being, when you control for that airspace, the performance between the clips and separate studs, at least based on this one comparison, is pretty darn close. So you don't rule out clips as an isolation method. And if you can use a thicker stud to get a bigger airspace or something like that, that could be a good option and reduce the amount of framing that you have to use. The other thing about clips is they can help with flanking. So we've got the sound going into the wall. So if you've got a double stud wall, the sound hits the drywall, and that's directly attached to the stud. So the stud's vibrating. But because there's this airspace between the two studs, this stud vibrating doesn't affect this one as much, right? But this stud might be probably directly attached to the structure up above. And so some of those vibrations might get carried up into the structure up above and then over and down or up into the room up above, all these things, these flanking paths. Now, we have other ways of addressing this that I'll talk about in just a minute, but one way to address this is just to reduce the amount of energy that gets into that stud in the first place. So if you have your drywall and then the drywall moves, but the clip isolates that motion vibration from the stud. So less of that gets into the stud. And then that affects, reduces the sound into all of those different flanking paths and the direct path. So something to consider. All right, so that's sound transmission. What about direct impact? Say you got this dude over here throwing medicine ball at the wall as part of his like CrossFit routine, right? I don't do CrossFit. But I think this is the thing people do. So if you've got this and you've got a noise sensitive space on the other side of the wall or up above, how do you isolate this, right? So you need to provide isolation to isolate that impact from the structure. But also you need to have a system that's robust enough to deal with that extra impact, right? That's going to hold up. So, I just talked about Rivet clip, hat channel being a way to isolate the vibration, sound in the drywall from the structure. But the drywall and clips alone is not enough to hold up to that kind of impact. So what you can do is, in addition to the RISC 1, so here we have the clips and the hat channel, you can put in between those the RISC 1 backer. And that's this thing. So it's a bigger, more robust piece of steel with 3 rubber isolators in it. And then you put a steel track over it. Excuse me. We often do this for mounting cabinets in like kitchens, things like that, grab bars in bathrooms, anything where you've got sort of heavy concentrated loads that you need a more robust substrate to attach to. But we can also do this in areas where we've got, high impacts and we need more durability on the wall. So you can put this and then put plywood over this. So you've got this plywood substrate to give you really your sort of like durability and impact resistance. And then you could put, an abuse resistant drywall over top of that. This works for fire. The RISC 1 backer is UL listed for use in any, I believe any wall that has the RISC 1 in it. And then there's a general provision within UL that typically you can put a layer of plywood behind the drywall too. So this works for fire, but it also works for airborne direct sound transmission, and also impact or isolate those impacts from the structure. So the last thing here is flanking. So again, say we've got this gym over here, we've got this unit here on the same floor, we've got this guy over here throwing his medicine ball at the wall. And so we're not just concerned about transmission this way, but we're also concerned with transmission to the space up above, because these units are stacked. Here's the units up above, these walls go up, right? So you could get this transmission up, maybe wall into slab and then into this other wall, right? So we can isolate the top of the wall. So this is a rubber isolator here that goes and attaches the top track to the structure. So it provides lateral stability, but it provides acoustic isolation. This is the PAC RISC U or the RISC U HD, and the RISC U HD specifically is UL listed for fire rated head of wall details. It's also included in some fire rated head of wall details with deflection track, and there's even a special deflection track that works. It's got a bump out to go with the RISC 1. So there's all these details on this, how you can make that work for fire and acoustics and construction and all of these things. All right, so we've covered a whole lot of details, got a little bit of time for questions here. Gyms, there's a lot going on. We got a lot of sound, a lot of impacts. A lot of different functions, a lot of different requirements for our flooring and all of these things in these spaces. So they can be very complicated spaces, and they can create a lot of issues with noise and impact and all of these kinds of things in a space. There's so many times I've been traveling for different conferences and things like that, where I've been in a hotel, like either in my hotel room or in a conference room, and I'm just hearing this thud, and it's from a gym. In fact, when I was sitting in my hotel room years ago, reading the Cyril Harris's book on noise control, studying for my NSPORT certification exam, I kept hearing thump, thump, thump. And I remembered seeing in the elevator that the gym was on the floor below me. I got in the elevator, went down. Sure enough, there's this guy in there lifting weights and just gently setting him down. He's on the floor below me. So that was like impacting the floor below, going up through the structure and then into my room. So that's the flanking path, right? So these things happen all the time. We really got to pay attention to them. There's a lot of details. Not going to cover them all or give you all of the answers in this presentation. I know I've thrown a lot of things at you. Point being, there's a lot to consider. If you want to talk through some of these things, please reach out to us. And yeah, now we'll turn it over for all kinds of questions.
Thanks, Mike. A couple of things popped up in the Q&A, and then we had some people making comments in the chat. So we'll cover the Q&A first. Let's see here. Starting from the first, Neil Shaw asked, at what height is the shot put release on your heavy impacts?
Currently, it's 0.5 meter. That's what's in the. That's what I did for all of these, and that's because that's what's in the draft heavy hard impact test standard that we've been working on for years. And I don't think that's going to change. I think it's going to stay a 16-pound shot put from 0.5 meter, and I think we're actually going to go through, whenever we can all find time, go through and do another round of that, make some changes, and hopefully get that balloted and maybe passed, fingers crossed. But I'm not going to hold my breath for that. It's been years and years we've been working on that.
All right, thanks, Mike. Next question came from Molly Smallcom, and she wrote, I found on-site mock-up 6 by 6 foot measurements will underestimate concrete floating floors because they're missing the mass needed to perform well. Does loading the system with sandbags help combat this? Do you have other thoughts on how to correct this?
Oh, goodness. Shorter answer is no, but let's have a chat sometime, Molly. I would love to get your input on that more. So in the ASTM draft heavy hard impact test center that I just mentioned, we have in there that if you're doing locally reacting floors, right? So rubber fitness tile or something like that, right? That even just like a 2 foot by 2 foot sample can usually be effective. And not to plug a competitor, but to give credit where credit is due. Plytech has done a bunch of work on that, and they've done things where they've taken a 2 foot by 2 foot tile, and then they've done like 4 of them and then 9 of them or something like that to see what the difference is. And there are some differences, but they're not big enough to really worry about it. Certainly not big enough to warrant, taking a whole bunch of like heavy rubber tiles to a job site to go do mock-ups. I am not aware of anyone, and maybe somebody on here will correct me. There's some paper presentation I've missed, but I'm not aware of anybody that's done something similar for like a concrete slab or even like a plywood floating floor, because it's just harder to increase the size of that. It's easy to just add more tiles, relatively easy. So I don't know. I mean, one way that you could do it, right, would be to weight it. And I have a whole bunch of vibration data and things that I'm happy to send you, Molly, and others, where I have unloaded and loaded, we have unsealed and sealed, we have all of these things. I've done some PAC presentations on them, and also I think ASA presentations. But I don't know. I think that's still like an outstanding question within the industry, and it's something that we need to figure out so we can do a better job with mock-ups.
All right, thanks, Mike. Let's see. Next question in the Q&A came from John Crichton. Back to the wall separation, or a double stud versus RISC 1. Which one will perform better in the field once all of the outlet boxes are installed? Double stud versus RISC 1 single stud.
I would say, I mean, I'll give the internet answer first. It depends. It depends on all these different variables. But I think generally that they would be, all other things being equal, the change in performance would be similar. Because the outlet box is putting a weak spot in the drywall. And if the drywall layers are the same for both wall conditions, like the impact is going to be the same. There is the potential with the RISC clips that if the contractor mounts the electrical box somehow rigidly to the drywall and also rigidly to the stud, that could create a short circuit. So that is an additional risk with clips that's not there with a double stud wall. But also with double stud walls, there's also a risk of like the contractors tying the 2 walls together, or just junk getting wedged in between them and connecting them. Like when I was a consultant, I would go do these site walks for a housing developer here in the Portland area, and they were building townhomes, and they had these wood frame double stud walls that went all the way up. And my job was to go out, inspect them, make sure that they were clean and constructed correctly, and then to videotape it as documentation, I guess, if they got sued down the road by a homeowner. I never went out and didn't find an issue with those. I always had to have the contractor fix things, and usually it was a number of things in one wall between these two townhomes. And oftentimes it was they had put wood blocking to nail the two top plates together when they framed them to hold them in place, and they just didn't take them out, right? So, and like that's not an issue that exists with a single stud wall with rivet clips, right? So there's unique issues for rivet clips, and there's also unique issues for double stud walls. So I would say they're both about equal in terms of potential construction variation that can affect their performance.
All right, thanks, Mike. And I see a hand up from Dave Yantic. Let's see if we can unmute your mic here.
Yeah.
You do that on your end? You got it, okay.
Yeah. Oh, I think I unmuted. Yeah, I allowed your mic and your camera, Dave. So now you can unmute yourself. Oh, not intentional. Okay.
All right, going back to the chat here, let's see. There were several comments as you were kind of working through some of your graphs. Let me see if I can get you back to where we were. Let's see here. Let's see. Farbad made a comment when we were looking at your impact noise. I forget on which graph, unfortunately. You would expect impact noise from weight drops would be within the lower frequency range as opposed to above 250 hertz frequencies.
Yeah, typically the bulk of the energy is below 250 hertz. I always kind of have an internal debate on what frequency range to show. I mean, for all of the stuff that we've done, because we're testing in labs and like controlled environments and things like that, we are getting good signal to noise ratio above 250 hertz. You'll notice like the vibration deltas, I truncated those at a much lower frequency than the sound pressure levels because with the accelerometers and things like that, we weren't getting as much like good data, after some certain frequency. But yeah, typically for heavy hard impacts and all this kind of stuff, it's all low frequency stuff. But sometimes it's just like if I've got the data and it seems like it's clean data, I'll show it so it's there. And then on the low end, also like I truncated everything I think at like 50 hertz. That's because I started with the Maxon data. Their lab, according to Jerry Lilly, I saw Jerry on here. I don't know if it's Jerry Lilly or not, but their lab is like qualified, meets the lab requirements down to 63 hertz. But the LIIC rating, which I mentioned, and I mentioned not to use for heavy hard impacts, but we use it for impact sound. The LIIC rating goes down to 50 hertz. So I used the 50 hertz band. And Evelyn, who runs the Maxon lab, like I talked with her yesterday and she was like, yeah, we still like my data still tends to make sense down to 50 hertz. So I kind of cut everything off there because it gets really messy and noisy below that. And while we do care about sound vibration levels below that, the data can get really messy. And so you can start to draw conclusions about things that maybe aren't real conclusions, actually.
And you're referring to LIIC then, basically?
Well, LIIC is just for impact sound measured with the tapping machine, and the LIIC is just defined
Not
as
heavy
the
impact,
tapping
yeah.
machine generated impact sound pressure levels in the 50, 63 hertz, 63 and 80 hertz third octave bands. So that's why I stopped at 50 hertz, because that's a metric that we have out there that goes down to 50 hertz partially.
Makes sense.
But that's separate from all the shot put data that I shared.
Different than heavy impact, of course. Okay.
Yes.
All right. Next comment came from Mariana. She said, caution, impact can also travel horizontally and vertically both ways, up and down. You don't just need to isolate for impact below, which is a good comment. She's correct.
Yeah. So yeah, and I guess I didn't explain that explicitly in this. So I would say that when we talk about like sound isolation and things like this, whether it's in a building or it's outdoor environmental noise control and things like that, you're trying to do sound isolation for a space like behind me or something like that because you've got some industrial noise site. We talk about we can do our sound treatments at the source, the noise source, the path, or the receiver. And sometimes there's, arguments for one of those over the other, right? So like if you've got a control booth for a piece of equipment that's inside a really big noisy factory, trying to control the noise from all the different equipment in that factory usually doesn't make sense. You just do a sound isolated noise booth. It's this one small little contained space and person goes in there, they need to be quiet, right? Other times, like when we have a noisy space like a gym, a spin studio, a fitness space, weight room, something like that, in a big building like an apartment or something like that, right? We've got all this noise in this space. It doesn't make sense to do a noise control for all of the different paths because of flanking paths, like she said, there's all these different ways the sound can travel. And it doesn't make sense to do our sound isolation at the receiver because that's every hotel room and conference room and office and all of these different things in the space. So we do it at the source and we try and keep as much of that sound, impact energy, whatever it is, in that space and try to minimize the amount that gets into the structure. So I kind of touched on that with like using the Rizik clips for a wall to isolate the sound that actually gets into that wall structure, right? That isolates the direct sound, but also all of the different flanking paths. But I didn't say that explicitly when I talked about floating floors and just the different fitness floors, right? So for heavy impacts, whether it's free weights or it's weight equipment or it's cardio or any of these kinds of things, we want to minimize the amount of that impact energy that gets into the structure. So like our first line of defense is always the floor. I mean, ideally, in theory, I mean, sometimes there's going to be other reasons why we can't do this or we can't do enough there. But like our first line of defense should always be the floor. So we minimize the amount of energy that gets into the structure because once it's in the structure, it's much harder to control, right? But oftentimes, if you have a gym and then a noise sensitive space like an apartment or conference room, ballroom, something like that directly below, the floor alone is not enough because that direct path is so direct and you get so much energy going that way. And so you need a ceiling down, isolated ceiling in addition to the isolated floor up above to get, a good level of isolation. But that ceiling only protects that space down below where the ceiling is. It doesn't protect all of the adjacent spaces. So yes, great point.
All right, thank you, Mike. There have been several other comments in here that were dropped in during your presentation. I would invite anybody who had more specific detailed questions about what Mike covered, because he just glazed over to the top of some of this, and there's certainly finer details if you're interested. Certainly, you can reach out to us and talk directly with Mike or send him an email. Yeah, but that'd be some of the questions at this point, Mike.
Okay.
Mm-hmm. Yeah, we had a question from Jerry about the cavity depth on the acoustical test on which was answered.
Covered that. Yep. Mm-hmm.
Dave just asked, do you use the isolation clip at the top of the stud on the bottom? I'm assuming, or on the bottom of the stud. And I was going to answer this, but I can do it verbally here. Dave, we have isolation products that isolate the head of wall and also the base of wall, so you can isolate one, the other, or both. And both of those are UL fire rated.
Yep. And if you've got, if you're trying to control the sound into the structure, you probably want to isolate the top and the bottom, unless it's maybe slab on grade for that lower one where you've got a thicker slab and it's kind of somewhat damped by the earth underneath it. Otherwise, you probably want to isolate both.
Yeah, and I'm dropping that product into the chat right now.
Awesome.
All right. Do we have any other questions, comments?
No.
No, I think that's it. All right. So there's quite a bit of information on our website. I don't know if you've checked it out. We do have a login if you want to access acoustical data, any of Mike's test data documentation. There is a login. Let me grab the registration here. You can register on the website. Mike will admit you, and then you have access to all of our test archives. We have assembly selectors and so forth. Let me grab this real quick. The computer will oblige me.
Yeah, and stay tuned. We have another webinar next month. Dave said more, please. So we have another webinar next month. I talked about Springs. I mentioned I've already done a webinar on Springs. This upcoming webinar in December, you can go check out the webinars page. We have always the next webinar coming up on that one. That webinar on Springs is a repeat for the most part of what I've done before. But there's a lot of information, a lot of details in that. So if you're interested in Springs, come check that out. I will have some new stuff in it too, because now I have some test data for our Springs. And we might also include in that a teaser for new high performance ceiling isolators that we are working on and hoping to launch next year. So stay tuned for that. Thanks everybody for attending. I know today is a holiday. If any of you are veterans, thank you for your service. And thank you all for taking the time today on what hopefully is a holiday for you otherwise to come join us and listen to me talk about fitness spaces and acoustics.
All right. Thank you, Mike. Thanks, everybody.
Thanks, Mike. Thanks, Steve. Thanks, everyone.
All right. Take care.
Have a great day. Bye-bye.